Today we're going to move on now to the topic which is on block diagram representation, which we started to meet a few times already. So this is how to formally address how we use it and how we simplify diagrams which help us to represent systems. Okay, at any point in time, of course, ask the questions and I'll try to answer them. Okay, so just again, a sort of reminder. It's always good to remind yourself why you're doing, why you are doing what you are doing, right? So the class, remember, it's essentially it's a background class and in a way a modeling class. But basically, what we do in engineering design, which is uh, what you do as an engineer, you have a problem to solve, is that you start off with a real problem, an actual thing that exists in the real world. And because solving it usually is not an inexpensive or an easy thing, what we try to do is to describe the model in a way that we could look and see exactly what is the problem asking us. So we model it and we test the model. And if the model seems to work to solve the problem, then we go ahead and we sort of implement it in real components. The real components being electric circuits and motors and pumps and valves and you name it, everything else that is in the physical world. But if it doesn't work, then we go back to the model and we adjust the model. We change parameters, we change values, and then we test it again. And we keep doing that sort of iterative work until we finally get something satisfactory. The modeling part, right? The modeling part here is the part where we use differential equations because as we saw, anytime you're dealing with, first off, electric circuits, anytime you're dealing with an electric circuit that has components that store energy, capacitors, inductors, or voltage supplies, those kind of things. Once you do that, now you're going to have something varying with time. And once you have any parameter varying with time, the description is going to involve some kind of differential equation, which is how our rate of change of time and so on. So we model it with differential equations and try not to make too many errors. We make certain assumptions, of course, when you're trying to convert from the real world to the model. And then you test the model. So testing the model means solving the differential equation. And how we usually solve the differential equation is to go into another universe where solving the differential equation is algebraic, addition and subtraction and division and multiplication. And that's where the Laplace transform comes in. And we do the testing of the model in the S domain. And we've started to see already from the properties of the Laplace domain that you could get from the Laplace domain, you get from the transfer functions, supposed to be poles, right? Poles, zeros, right? And the poles, remember, the poles are the ones that give zeros shut down the system because they're in the numerator. The poles are the parts where the transfer function tends to go to infinity, which will mean in a real world it would go to whatever the maximum power supply will allow, or it will rev up to the maximum, or a valve will open to the maximum, that kind of thing. So the S domain work, already we've started to see that just simply by solving the differential equation and looking at the poles and zeros, you can already get an idea if the system is going to be stable or not. And then when we looked at first and second order systems last week, we saw that a first order system where the poles will give you a fast transient response or a slow transient response and the like. And on a second order system, we saw that if the poles were in particular places and associated with that were things like a gain and something called a damping factor, that you can get oscillations. Now, if the model of the system requires you to have oscillations, then of course that is what you would do. But if it doesn't, then you have to adjust the parameters, and we saw that you could vary the damping and vary the gain and the natural frequency and so on, and until you get a response that you like. And that was one of the last things that we discussed last week. And then once it works, of course, you go back down to the you come back out of the Laplace domain, and the answer that you have there now is something of a function of time, and the coefficients and so on would relate to the real world components and so on. And of course, everything in the blue square is we use all of the simulation and modeling tools that we have at our disposal. So you could use plain pen and paper mathematics, like the convolution, if the input and outputs are fairly straightforward, or you could approximate them to that kind of thing. You could use things like MATLAB, where you have the MATLAB environment, or you have the Simulink environment. And there are other computer simulation packages around as well. So like in electronics, for instance, we can use multisim. In power systems, those of you who go into it, they are modeling programs that allow you to model power system behavior and so on, right? So a lot of words to sort of bring us back to the real world, that while we are doing, a lot of fiddling with models and the like, there's a reason behind it. And hopefully when you go into things like a final year project and so on, you will remember that okay, I have something to do, but let me develop the model first, and then test the model first, and then you go and you build it out. Yeah? So one of the ways that we model systems, apart from the differential equation, or using the differential equation, is to use something called a block diagram. Now, what you have on the screen there is something that we met a few times already, which is an integrator. And an op-amp integrator is an analog circuit that can actually solve the differential equation down at the bottom, right? So this is the input-output relation for that op-amp upstairs, but it is solving, it is integrating for us. So it is actually, we can do an integral. So if I have a differential equation, for instance, and I pass it through the op-amp, it will integrate the differential equation and solve it, which is how you solve a differential equation. And I mentioned kind of on the fly that many years ago, when they put people on the moon, that this is how they actually control the differential, they solve the differential equations that control the rocket flight while you're going up. Aerodynamics and rocketry and so on, the control of the trajectory is a lot of differential equation mechanics and so on, that control how the spacecraft functions, the stability of the spacecraft functioning. So every time you make a change somewhere, a differential equation has to be solved before the control system can tell the engines what to do. And they didn't have computers and they like, at least not small computers enough to fit on a spacecraft. So what they said is, okay, we will use electronics, actually analog electronics, to solve the equations. And this is what essentially they did, and they were able to, as I say, safely land people up and down. And in fact, in some old control systems, it is still done this way. If R and C are fixed, then within reason, you could keep solving the same differential equation all the time. Once the input and output changes, once the input stays within some range, then you could keep solving the equation all the time, literally in an analog way. All right. And again, so just let's sort of model it and so on. So if you can see, just sort of amplify the point that you can implement an entire equation, a differential equation, using integrators and other components like summing arms and the like. So if you take your typical first order differential equation, which is this one here. right? We have both coefficients for, or first derivatives for x and for y. The most general form, y is the output, x is the input. So we put everything in terms of dy dt, in terms of everything else. And then to solve this differential equation, what you have to do is integrate with respect to time, and you'll end up with the equation down at the bottom. Normally, if you had to do that and you know what x is and you know what y is and so on, then you have to go through, if you didn't have the Laplace transform, you have to go through things like, integrating factors and those kind of things mathematically before you're able to do that integration. So we could draw this out in a diagrammatic form. If you look at what I've done in the diagram below, the equation is actually two parts. Yt is b1 xt, and then the other part that deals with an integral of the things, of the two expressions in the square brackets. So if you look at what we have here, the part in the square bracket, we have b0, right? And then we have ayt. So we have yt and we have something, and we have a coming back inside of here. Ayt, and we have a minus sign. So coming out of here is b0xt minus ayt, and we pass it through an integrator, which is the same op-amp that they had, and then we send it down here. And then the other part is b1 x, and then we add them up, and we actually have the in terms of a sketch, we have it sort of drawn out. And then if you start to put in the things that we know, a circuit to solve this, for want of a better term, the integrating amplifier, we have it sitting down right here, which we just saw. This is an inverting amplifier here because it's taking y, multiplying with a, and giving you a minus coming out. This is a summing amplifier, so it's going to add those two. This is a summing amplifier here. The B1 on top is a non-inverting amplifier. So in fact, I could sit down with a breadboard, some op-amps and some components, and literally wire up a hardwire circuit that will take X and give me the solution Y once I have the values for A and B1 and B0 inside of here. Yeah? Nothing strange about that. Probably not something that well, we mentioned it before, but it's not something that you think of offhand when you were doing op-amp integrators. You use it you know it integrates because it's working with a capacitor, and that's the relationship with the voltage and current in a capacitor, but actually using it to do mathematics. And we could do this thing, we can keep expanding this down the road now. So if we go up now a second order differential equation. The second order differential equation has second order derivatives in both y and x. And therefore, whatever answer you're going to have to solve for y, you're going to have two sets of integration to do now, right? So you have the double set to get rid of the d2y dt squared, and then the single one because we have a dy dt inside of there somewhere. And if you do the same thing that we did before, you start from the inside here, the little bit in green here. All right, so you start with this bit here. Once you start with that, and then you go backwards. We did this bit already. That was just now. And we add the extra integration on the other bits on top here. So here's a model now of an electronic system. Again, how many we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 op-amps. Right? Sounds like a bit. You could get four op-amps on a device, so you basically have to have 3 other devices, some resistors, some capacitors, and some wiring. And you put this down, and you have a circuit that solves a second order differential equation, a fixed second order differential equation. You can't go changing B and A sort of randomly, but they, at least for some range of X, it is going to give you an answer for Y coming out. Yeah, make sense? And we know it works because they sent how many? What, 15 people to the moon, 10 people to the moon? I can't remember the numbers, somewhere between 10 and 15 actually went up to the moon. A few of them landed, drove around, and came back safely. And they didn't have microprocessors, and they kind of, even the handheld calculators that you have, they didn't have iPhones and anything like that. So we know it works, yeah. And it's something even you could design now, right? Why isn't two integral signs used above a0? Since it's a double integral. Right. No, what we do is that we integrate and then we integrate again. If you follow the a0, let me go back by a0. A0 is, hold on, let me just backtrack here a little bit. A0, right. A0 is actually being integrated twice. Remember, look at the thing. So it comes through here, it goes through the first integral, then it has to do something else, and then it's integrated again. Right, so this is actually the double integral here, but in two consecutive parts. If you watch where it has to be first multiplied by y, then added to something, integrated, and then integrated again. Right? Right? Just trace a line through. You'll see it is being integrated twice. It's how it's a flow of the process. So if you look at it inside of here, once you get a0, then you have to multiply by y first, then you have to subtract the input and integrate once. Okay, and then you go back through and then you integrate it again. You know, so it's right there. That does trace it through. Of course, if I made a mistake in the diagram, let me know. Okay. Right. So what we can do now is that, of course, we can apply the Laplace transform to the block diagram. The Laplace transform of a constant is unaffected, and the Laplace transform of an integral gives you a 1 over s operator. Now, I've put 1 over s inside of here, but more correctly, it is a 1 over s operator. It's more correct to say that it is a 1 over s operation or operator rather than 1 over s, right? The Laplace transform of the integral sign is not, or the integral function is not 1 over s. It's 1 over s times something, right? It operates on something, but it's good enough to illustrate what actually is going on inside of here, right? And then so therefore, if you follow through the diagram, and you add it through, so you will have coming back from, let me get a different color here, right? So from y, so here would be ays, right? Here you have, sorry, at the endpoint here we have b naught xs. So at this point here, of course, you have b naught xs minus ays, right? And then you multiply that because the operation will be a 1 over s on that, right? And then you're adding it up to b1s here. So if you put all of that together, and then you get y on one side and x on one side, you get that the block diagram now simplifies to b1s plus b0 over s plus a times the input. You always want to get it in this form. So this is the transfer function here, right? And y and s are on the other side. So it's a diagrammatic way of representing it. And there are software functions, for instance, MATLAB Simulink will allow you to model a transfer function in this way. so that way you can manipulate the variables, right? So we're now starting because as you go in now, you will see where this is useful, but how it allows you to continue the whole modeling process. So in general, the overall sort of grammar, if you like, for the block diagram is that the block diagram is an S-domain representation, a Laplace domain representation. All of the manipulations that we're going to do are done in the S-domain. And so that once you simplify now, if you require, then you can convert the equation back into the time domain if desired. And later on, when we study some, there's a couple of lectures we'll do on something called stability. You will see even at that point in time, you could get an idea of the stability of a system without even going back to the S domain at all. Sorry, to the time domain. So you could do everything in here, which is what the beauty of it is. So some simple examples then. Here I have X. I have an HS now, which is our block. So it's 1 over S plus 1, our first order system. So Y is H by X. Remember, this is in the S domain. In the time domain, Y would be H convolved with X, right? That's the input-output. The real world is a convolution world. So the input-output relationship of all systems in the real world is convolution. But in our case, the convolution transforms into a multiplication process once we go into the Laplace domain. So right off from here, so we see Y is 1 over S plus 1X. Fairly simple. But from, I mean, it is a trivial example, but just to show how the process works. So now we can start to get a little more complicated. So here's a system that is called a parallel interconnection. So X is coming in and it is going to two blocks of the system, two internal modules of the system for argument's sake. One has a transfer function, 1 over S. The other one, in fact, both of them have the same transfer function as it's turning out in this case. So the output Y is a combination of both the output Y2 and Y1, right? Y1 is X H1 and Y2 is X H2. And we could do all of this thing because we're dealing with linear time invariant systems. Remember, we spoke about that very early on. It allows us to split systems up and add up the answers. If they're not linear or they're not time invariant, right, then we have issues doing these kind of behaviors. This is done, in fact, when you take a transfer function and you express the transfer function into partial fractions. You remember what you do if I give you a transfer function and I ask you to express it into partial fractions, you normally have some complicated thing. Let's say Sx squared plus Bs plus C, and you would have it now into some constant over S plus D, let's say, plus some other constant over S plus E, for argument's sake. So you have taken a transfer function, and by applying the partial fraction rule to it, you get it into two parts. So any input coming in here is multiplied by these two things individually. What expressing in partial fractions does, therefore, is to convert a transfer function into a parallel form. Yeah? Make sense? Right? Okay. The other one now is this. So you have a serial interconnection now where the transfer function, the input goes into some module. The output of that module now is input into a second module, and then the final answer comes back out. This is now known as a cascade interconnection. And this is, you get this sort of arrangement if you want to have a transfer function and you want to see what the cascade interpretation of it is. This is what happens when you take it and you express the transfer function in poles and zeros form. So you remember in that one, you would have the transfer function, which would be like a as squared plus bs plus c over ds. Okay, I'll put squared here. Technically, it shouldn't be. Plus es plus f for argument's sake. But when you do this now, what you do is that you get it into you get a s plus g and a s plus h and whatever other letters of the alphabet we have downstairs below. We have s plus, I don't want to use I and j, let's use k and s plus l kind of thing, right? This is pole zero form, so these are my zeros on top here, my poles here. So I could break this up now into this. This is, if I just drag this out a little bit, right? This is open, bad color, right? This is s plus g over s plus k multiplied by s plus h over s plus l, right? Which is this one. So this could be a h1 and this could be a h2 here, right? So by breaking up the thing, those sort of drudgery exercises that you learned from way back when, and then you did with Laplace transform, and we touched on in revision here. When you take a transfer function and you express it in pole zero form, you factorize it, the denominator and the numerator, you have now expressed the transfer function in a serial or in a cascade form. Why you'll want to do that is, again, the modeling part of it. This is a lot easier to deal with than the whole, what do you call it? When you put everything together and you have a big complicated transfer function, it's harder to deal with in terms of changing components to see what works and what doesn't work. But if you break it down into smaller components, I could very easily change a coefficient here or a gain here or something like that and see how the system behaves. Yeah? And most things, that is what you do. You take the system, or you will take the design, or you're given the design, but the design is in a very modular form. Yeah? And you work in the modules, and then you go back up the sort of complexity ladder, if you like. Right, so feedback. So here's a block diagram with feedback, and there's a 4th time we're meeting this. So by now you should know this fairly good. What kind of feedback is this? Yeah, right, that one, no brainer, right? So you should pick up that one and look for the minus sign on the feedback loop. That is this guy here. This is the feedback loop, right? One of the little things you're going to see later on as we do the more complicated block diagrams and simplifications is sometimes the feedback loop wouldn't always be here and it wouldn't always be called H, right? But you have to see something that is coming from the output to the input, back into the input, right? So, and again, if you simplify this, what should be the simplified version of this? Y over X should be what? By now we should know this. For negative feedback, it should be right. So everybody flying back now to see the notes, right? G over 1 plus GH, nice, right? So because it's negative, the output is going to be GS over 1 plus GSHS, right? Or as he said, sometimes you just say G over 1 plus GH, right? Always remember it's a function of S. This is acceptable because sometimes it's tedious to keep writing G of S, H of S, and that kind of thing, especially when you have G1, G2, G3, and the like going around the place, right? And then what I've noticed too, it happened to me sometimes as well to a simplifying, and you have GS, right? And then you start making the S funny, and then all of a sudden the G, you forget the bracket and you have something looking like a 5, right? And so all of a sudden G5, and you might have a block named G5 and the whole thing goes crazy on you, right? So sometimes maybe it might just be simpler to write G over 1 plus GH. That is acceptable, all right? So yeah, so if you didn't remember that, you could go through and follow it. This is a formal derivation of what we had spoken about a few times before, right? So a closed loop feedback system, that's a formal definition of something like that. Closed loop because this loop, right, there's a feedback and it's closed. It's going on, it's a continuous loop, right? So it's a closed loop feedback system. And this particular example had negative feedback. And we saw for positive feedback that the sign here would be negative. All right, so G over 1 minus GH in that case. Right, so here's one, and this now it starts to show you how it works. So G is 2 over S plus 1, H is 1 over S plus 3. So two first order systems, and remember first order system could be something like a simple RC network, for instance, where we would give you a first order differential equation. And you put the two of them together and notice that with this particular one, that ys is now 2s plus 6 over s squared plus 4s plus 5. So you have a system, the two, whatever they forward block, the G block has a transfer function 2 over s plus 1. However, that whatever the problem is, give you that. And HS, the feedback, had a transfer function of 1 over s plus 3. Okay, so the overall thing, you just combine it, G over 1 plus GH. And if you don't make any mistakes, you're supposed to get the answer 2s plus 6 and on top of s squared plus 4s plus 5. So there you could look at that. And then, for instance, now we're in a situation, what is the step response of the system? All right, so to do that, xs is 1 over s, and we call how you do it. So you now do that and you expand into this. And well, here's the question. What are the nature of the poles in this? Bearing in mind what we had spoken about before. Right? What kind of poles do we have? Do we have simple poles on this or complex poles? First of all, how many poles do we have in this? Nope. 3. We have 3 poles. No. 4 is too high. Right? We have, look at the order. When I expand this, I am going to get, if I were to expand this out, I would have s cubed down at the bottom. Right? So if I have s cubed down at the bottom as a maximum order, this system is going to have 3 poles. I have an s on the top, so it has 1, 0, and 3 poles. Are they poles? What kind of poles do we have? Are they simple or are they complex? Right? Somebody saying simple, well, don't guess. Remember what the poles are. The poles are the roots of this thing here. The roots of the denominator. Right? If you look at this, forget the top for the time being. We have the numerator. The denominator is going to be s into s squared plus 4s plus 5. If I split that up into partial fractions, I'm going to get something over s plus something over s squared plus 4s plus 5. What are the poles at that fit? So we already have one simple pole here. That is a pole at S equal to what? K over S is a pole at S equal to 0. Right. So what about the other one? S squared plus 4S plus 5. Well, what are the roots of that, which would be the poles, therefore? The other poles. What are the roots of S squared plus 4S plus 5? Real or complex? Right, complex. Right, to find the roots, you could just apply the quadratic formula, and already you're seeing that b squared is less than 4ac. So that's going to give me complex poles. And complex poles, we saw that here. If you have complex poles, then you're going to have decaying sinusoids, either sines and cosines, sines and or cosines appearing. Right, everybody following? Right, this is kind of revision, but we also interpreting it here on the fly. So you should be able to watch something now and with a little bit of manipulation now, watch the thing, see how many poles, how many zeros we have, and if the poles and zeros are complex. So you plot it out. Right, you plot it out and notice the two complex poles here and here. As somebody said, the poles are at, what do you call it? -2 plus or minus j, right? -2 plus or minus j, right? And we have a 0. There's a, where's my origin here? Sorry, the 0 is at here, right? We also have a pole here, a simple pole at the 0. I should have put that there. Right, but outside of the excess, the transfer function itself really has 2 poles alone. The solution has 3 because of the 1 over S part of it. Notice this here, how the simple poles can combine to create complex ones. Remember, each block, let me just go back a little bit. Each block here had a simple pole. This was at S equal -1, this was S equal -3. Both of them are stable. They're on the left-hand side. Remember speaking about that? If a pole is on the left-hand side of the S-plane, that the system should be stable. So you sit down, G has a pole on the left-hand side, H has a pole on the left-hand side, so both of them are stable. You combine them, and then all of a sudden you get complex poles, right? Complex poles, it just so happens that the 2 poles again are on the left-hand side, so the system is going to behave stable, but they are complex, which means that you have a sine or a cosine appearing. So the response is going to, you remember when we spoke last week Tuesday about second order responses with complex poles. Depending on the value, the step response, which is what we're looking at, right? The step response can do this, right? It could do this, right? Those kind of things, right? Or it could do this, right? And if you plot it out on the diagram, this is the kind of response that we have. So what would you say that response is? Is it overdamped, underdamped, or critically damped? And what does that have to do? When I'm talking here, remember in the second order function, this had to do with what? The value of something. Remember last week we spoke about it? K or zeta, correct, right? The damping factor, zeta. So if the zeta was, what was the sort of range that we were looking at? If it was overdamped, what does the response look like? And look at it, plain English. If you damp down something, you sort of smother it. So if something is overdamped, it means that you're smothering the response. You're trying to hold back the response. So the overdamped, if the response is overdamped, the response will try to do something like that. It's smothering it. If it is underdamped, then what would the response look like? Yeah, hold on, Stephen. We'll see exactly where it is. If it is underdamped, then it means that we are allowing the oscillations and so on to occur. So exactly, right? So if it's underdamped, it's going to, oops, underdamped is going to do this kind of behavior for me, right? And if it is critically damped was the behavior where the response basically just before it went over. Anybody remember what we call that? Overshoot, right? Right, so when the response, this looks like it's supposed to settle along somewhere by 1.2, it flies past that, so it goes up beyond it, and it's what we call overshoot. So when the thing is underdamped, you get a lot of overshoot. When it's overdamped, the response is suppressed. And when it is critically damped, the response is absolutely, it is just before it starts to overshoot. So this is kind of like what you're trying to aim for in most cases, either this or underdamped, right? So the response here is one of these two. If you were to actually zoom into this, right, you can't see it here, but if you were to zoom into it in this area here, you would see it slightly goes above, you kind of zoom it, it just goes slightly above the 1.2 line. Right, so in fact, this one is underdamped very slightly. Right, it is slightly underdamped. But just giving you that, if you were to tell me it's critically damped or underdamped, both answers would be correct, but you could work it out. You remember K, you know what the value of K or zeta has to be for it to be critically damped. That's in the notes last week. Go and revise it. But so that you could, although you have the diagram here, you could actually calculate what zeta is right now. And depending on the value, you could tell me that is okay, is underdamped or is critically damped. Yeah. So again, we sort of put everything together in one example again, which is why it's important to revise this material and don't let it build up on you too much. All right. And then, of course, I'll leave you with this to try and see what happens here now. Let's do this one with positive feedback. So what's the transfer function, the general form for the transfer function for positive feedback? You know, you have a G and a 1 and a GH here. So for positive feedback, it's going to be what? Minus, correct. Right? So G over 1 minus GH. So substitute these two now and see what YS is. And doing the same process again. What is YS? Check and see what the poles of YS are. The transfer function itself has two poles. If you have an input of excess, whoops, a step input 1 over S, then the solution going to have an S and the two poles there inside of it. But the transfer function itself has two poles in it. Okay? Two poles. For that, look and see where the poles are and look and see what the effect of the positive feedback is now. All right? It wouldn't be, we haven't done how to do a step response using MATLAB, but you could try it out, right? To plot it out and see. All right, so questions. This is an introduction on how to manipulate the block diagrams and what they actually do. Tomorrow now we're going to see how when you have a nice complicated block diagram now, how you could get it down. The goal is always when you're given a block diagram to get it down to to get the entire block diagram into a simple, all of the forward blocks into one forward block, all of the feedback blocks into one feedback block, so then we can now finally simplify everybody using 1 plus GH. So we use this repeatedly through, as we will see tomorrow when we start to simplify these things. As we go through, we're going to simplify using this and some other little manipulations, and then you simply then you put down everything together. You simplify the thing. What was that question? Which slide? How you got GS being 2 over S? That's not. Which slide are you talking about? This one? Yeah. No, you're given that, right? This is an example. So somewhere along the road, you've been given these two things, right? We didn't derive it anyway. In time to come when you're doing like your controls and other things like that, you might actually have to derive that. So like a motor, for instance, has a known transfer function depending on the inertia and the horsepower and that kind of thing. A valve has a particular transfer function, and so you go on. A temperature sensor will have one, right? Yeah, don't read anything more than what we have, right? We know we're not surprising you by putting in things that haven't been explained. All right. So any other questions? All right. The updated slide for this was uploaded, right? So you could so if you had downloaded the original one that I put up since last week, you could kind of just replace it with this one. The only difference is that it has some extra writing just to reinforce what we spoke about in class. All right. So next time we meet, well, I'll meet some of you all this afternoon for electronics and the lecture with Dr. Radix and so on. So we'll go through that. And tomorrow afternoon, now we're going to look at how to simplify block diagrams and try manipulating a couple of them while we're in class. All right. So if everything is fine, I will end the recording here. And